I'll say it now in case I forget, but if you've got any comments about being here, do let us know. But not now. If you could email any of us afterwards, any of the committee, that would be good. So I'm going to give you a synopsis of the fire procedures, which I won't do every time, but it says don't attempt to extinguish a fire if untrained to use firefighting equipment, and if you hear the alarm, do not panic.
That's the bad.
And basically, leave the building by the nearest available fire exit. Don't stop to collect personal belongings or use the lift. I'm not sure how you get out if you can't use the lift, but some do.
Stairs by the loo.
Both ends. Stairs both ends. And the assembly point is at the corner of Exeter Street and the Strand, and Exeter Street is the next street along. So it's quite simple. But now I'd like to welcome our speaker with the presentation today called Proposed Computers, Several Design Projects That Never Left the Drawing Board. And our speaker is David Eglin. I'm delighted to introduce you, David. And David worked at ICL for 20 years when it was first Ferranti, then ICT, and then became ICL. And he's told me that Chris Burton was David's boss at ICL. And David was responsible for the design of the 2980 computer. So over to you, David.
Okay, can I just say two things before we start? I was responsible for the design of the 2980 CPU, not the whole conglomerate. And also, I think there's a rumour going around that it was just a copy of MU5, but it wasn't at all. It was nothing to do with MU5, but just say that. And also, I'm going to kick off with an apology because some of the things here I have a very slight personal touch on, very slight indeed. So if I refer to myself, I apologise for that. So apparently some people refer to themselves as the lecturer, but I'm not going to go there. Okay, let's really start. Here we go. I couldn't think of a title for this, which is why I think it was you, Roger, who dreamt of the title.
Not that title.
No. Well, this is the best I could come up with. But a lot of these things did leave the drawing board, and some of them in vast quantities even. So let's make a start. Now, the various themes turn up as you are talking about these things, and by far the most important one is Moore's Law. It's something which is hovering behind everything that went on after about 1975, because it was obviously going to be true, and it didn't colour a lot of people's activities, but it was always there lurking in the background. The Wheel of Reincarnation was a paper written by Evan Sutherland, and what he talks about is the movement of intelligence from the mainframe, a single computer somewhere with terminals, dumb terminals, and then the intelligence moves out to the dumb terminals, and then somebody says, well, we could do all this in the mainframe, and it moves back again into the mainframe. It's a really good article, well worth digging out and reading. And also, as we go through, we'll see that different management styles produced vastly different results. And in some cases, the relevance of what was going on and whether there was a return on investment or not was not considered. And in a couple of the projects, there's hubris at the end of them. Plenty of others that I don't know about. Okay, so let's move on. Now we have to start with Babbage, of course, because that was another, the first undelivered machine in Britain. And I've talked about this before the last time I was here, so I don't want to spend a great deal of time. But since then, I've read a book written by a Swede, and I'll show you the book list at the end of this when we hand out the test papers. And he's talks about the Schutz, if that's the right pronunciation, and various other people, and Babbage. It did strike me that one of the problems that went on in Britain was that we didn't have any technical education. There was a technical institute founded in Stockholm in 1798. There was nothing like that in the UK. The education system was apprenticeships, and the University of Engineering was Maudslay's workshop in London, where not all the great engineers went through, but a lot of them did, and certainly Clement spent a lot of time in Maudsley. So really Babbage hadn't got any choice. He couldn't go to an academic establishment and say, what's the best way of tackling this? I think it should have been the clockmakers. Whereas in Stockholm, Schutz was a very clever person. His son went to the technical college, and his son just got stuck on with making it without any great fuss. Whereas Clement was interested in his own aims rather than what Babbage wanted him to do. So that's all I'm going to say about that. But this book is well worth reading, and I hadn't read it the last time I came here. Now the first thing I'm going to talk about is not really what we've got on the screen here. It's about something that went on at the same time. Sometime, must have been around about 1965, two of us were asked to put together a proposal for a dual 1904. And one of the problems with something like this is that you've got two independent inputs to something, and there's an asynchronous problem. These two are not synchronized, and you've got to somehow sort that out. And the solution we came up with was simply synchronize the clocks into two CPUs. That would have been quite easy to do, and that gets rid of the problem of asynchronism. Now at this time, I had somebody in the lab at West Gordon who argued with us over this. He said, it can't be a problem. There is no problem with this sort of thing. And we poo-pooed him, and that was really the end of that. But why did we know there was a problem? And it goes, it didn't show up very well. When we first got I think it was just the drawings of the FP6000, which became the 1904 in West Gordon, somebody looked at these drawings, and he looked at the circuit which where the peripheral channels came in, requesting access to the memory, and there was a circuit, which is in this box here, which sorted this problem out and allocated the access to one particular peripheral. And I can't remember who did this, but he looked at this drawing and said, I'm not quite sure that's going to work. And so he built a rig on the bench, which fired accesses at random again into this circuit, and eventually it went wrong. And this is how in West Gordon we knew about this problem of asynchronous things causing problems with flip-flops. And a good few years later, I went to a talk by Ian Barron, and he said, you know, one day we discovered that flip-flops could sit in the middle and go wrong. And it suddenly struck me then that all over the world, people were hitting this problem, saying, oh my God, I didn't know there was a problem here. Now, of course, every CS course in the world probably runs a course on this, but now we didn't know about it. And there were still a lot of deniers about. Just very briefly say what the problem is. If you take the perfect flip-flop, sorry, I can't point at two ones here. You have to let the data settle down in, one way or another before you apply the clock to the flip-flop. And this time between the data settling and the clock is called the setup time. And if the data moves into this setup time, then if it was a perfect flip-flop, it might or might not set the flip-flop, depending on your luck. But if it's a real flip-flop, what can happen is that the flip-flop output sits in the middle, and it sits halfway between the two voltages, and this can go on forever. Not very often, but it can cause a problem. And there's a guy called Molnar who's, in fact there's even a video, I think it's probably on YouTube, where he talks about this, And he wrote a paper about it, and the reviewer said, as a denier, he said, this problem can't exist. I know, I'm an expert, and it can't possibly exist. And we've all met a few of those, I suppose. Why have I called it colliding ships? Chris might correct me on this, but I'm pretty sure this is the story. That when this problem was found in West Gordon, Ken Johnson, who was one of our resident clever people, said, oh, it can happen all over the place, even colliding ships. The rule of the sea is what we've got up here, but if ship B moves down a little bit, you get to the point when they can't decide whether they're going to pass the other way, or pass the official way, and they can collide. And I'm sure that's happened. Not the origin of the story, but the oldest part of this story is the story of Buridan's ass, where the ass was presented with, in this case, a basket of food and a bucket of water, and he sits there forever trying to decide which one he's going to take first. Sometimes the story is 2 baskets of food. In this particular drawing, there's food and water, and this goes back, I don't know the origin of it, it goes back all the way. Ian Barron again, I'm not 100% sure about this, but I think this is the case. You've got an even bigger problem, of course, if you join a lot of computers together, which is what transputers were meant to do. And I think the Ian Barron solution, probably brought out of his earlier experience, was to have a synchronizing clock which went everywhere, and the computer clock was not a subdivision, a multiple, a faster frequency than this anyway, so you could synchronize the CPU clocks with this master clock going around through the whole system, which eliminated all the problems of communication. So this isn't about computers that didn't leave the drawing board. I thought it was worth just saying something about it. Okay, first computer. CDC 66000 was really a seminal machine. So woke everybody up. And Mr. Watson Jr., head of IBM, wrote a memo, and it's the famous memo saying about, it's called the Including the Janitor memo, where he wrote a memo saying, how can CDC with 34 people, including the janitor, produce a machine like this when we can't? And he then wrote another memo saying we should go for broke on this and produce the fastest computer in the world. And this was called the IBM Advanced Computer System. As you can see from my dates, it didn't last very long. It was an extremely complicated design, and I don't think the design was ever finished. There are some sketches of bits and pieces of it. The hardware was even more ambitious, which we'll come to in the next slide. And there was a guy called John Cock on the team, who was a sort of roving ideas man. He wasn't the head of the team. The team had a proper technical head. There were a lot of people involved. And this went on, and Amdahl got involved. I think by that time he was an IBM fellow, which probably gives you the right to do pretty much what you want. You don't interfere with everybody's project. And he became ostracized by the team who was interfering so much. But he did persuade the management that this thing should become a 360 compatible machine, which it wasn't initially. It was going to be a new type of design. But then the management cancelled it. So he won his argument, but lost the battle over this. Then he left IBM. And I once went to a lecture by Amdahl, which was a really very interesting lecture. And he said the reason why he left IBM was because of the legal papers which were put into the court when CDC sued IBM, didn't they, over this? And the IBM management had to reveal their thinking about big computers. He looked at these papers and said, you know, I don't agree with the thinking. I can make something which will sell above the top of the 360 range. And in this lecture, he didn't mention this ACS system, maybe because it was meant to be secret. I'm not sure about that. So let's look at the hardware first. Now, I'm sorry, the pictures here are extremely fuzzy because this one and only remaining circuit's been potted in plastic for some strange reason. So we're looking through the plastic to see this. And this is where the ambition comes in. This is a tiny little printed circuit board. It's only 1.25 inches, 24 chips with enormous heat sinks on them. And underneath the heat sinks are ECL circuits with, as I said there, 20 gates on them. So the packing density of the circuits is extremely high. And this, all sorts of crazy things were told. This thing had to be a wired machine, no printed circuit wiring, because the wires were faster than the printed circuit. And they devised a means of ultrasonically bounding these wires to these little tiny lands on this board. And what they were after was a 10 nanosecond clock time, which, if you look at this table here of clock times of machines at the same sort of time, was, you might say it was a ridiculous aim, I don't know, but I suppose Seymour Cray managed 27.5 on the 7600, but it was a really crazy aim. And of course it's had to go in to be liquid cooled. But again, there are videos about this. They had a big reunion in the 1990s, these guys. One of them, the technology guy, tells a story of the coolant leaking one day, and apparently this stuff cost more than malt whiskey. So they lost something like the price of a big car of this leakage that they had, this coolant. I'm not sure whether this was the final idea about the board, but there is a bigger board with 620 odd chips on it. And I don't know whether this was meant to be the final design or the bigger board was meant to be the final design. But it was you might call it a ludicrously ambitious aim. And it got cancelled in 1969, so there we go. The design had in it 300,000 logic circuits, much bigger than Stretch. The CPU design had everything but the kitchen sink in it to try and improve performance. Lots of pipeline to cope with the 10 nanosecond cycle time. You can't get much done in 10 nanoseconds. And Lynn Conway, who was the Conway of Leading Conway, wrote a long paper about doing a multi-level simulation to try and verify the design. And it reads very well, this paper, but whether it was, again, whether it was practical or not, I don't know, because what sort of processor are you going to run these things on? It's the perennial CPU designer's problem. If you're trying to design a big CPU, you can't simulate it because there isn't a much bigger CPU around to do the simulation on. And we did tinker around with multi-level simulation in West London at one time, but it came to nothing. Probably because I was slightly involved, but there we go. And Thomas J. Watson said IBM should go for broke, and one suspects that this would have gone for broke as well had it gone any further. It was extremely ambitious. Now the next thing is much more comforting. This is the Xerox Alto, and one of my colleagues in West Gorton left ICL and went to work for Xerox Park, and he went to the El Segundo branch, not the Park branch. And I got a demonstration of one of these when I went there. But first of all, let's talk about what happened before Park. There, and I didn't know about this before I started reading these things, but there's apparently a very famous paper written by a guy called Vannevar Bush, who was the originator of the mechanical analog machine that was brought over here. By whom? Come on, somebody tell me who brought it over. Hartree, yeah. But he wrote this paper, which I think appeared in a magazine, about what the future should happen, or should give us. And everybody refers to this paper. And he invented a machine called Memex, this is a picture of it. And he was obviously a practical guy because he built this analog machine, and this was his practical solution to information technology, and it was all driven on 35mm film. You could input things which then got recorded on 35mm film. You could read them back on 35mm film. But this was 1945, of course. We didn't have any alternative at that time. Apparently he inspired Ivan Sutherland when he did the Sketchpad. His PhD project was Sketchpad, which earned him the nickname of the whizziest whiz kid of them all, and went on to do other things. And we're getting closer to Xerox PARC now. He also inspired a guy called Doug Engelbart, who was at Stanford Research, and he had this lab called the Augmentation Research Center. And on YouTube you can find a demo called The Mother of All Demos, 1968.
I was there.
Sorry, what was that?
I was there.
What, were you? You should be up here, Chris. Were you one of the cheering crowd, though? Were you impressed?
Yes.
Oh, right, okay. And in a sense, it was all kidology, because he'd got all these guys back in somewhere that was networked to his, not networked, there was a microwave link or something back to his lab. But he demonstrated word processing, hypertext, which I think was invented at Stanford. He certainly demonstrated the mouse, which he invented. And there was this networking. You could, I've not watched the whole demo, I must admit, but one of the things he had was he was talking to a guy who also had a screen, and they both had a spot on the screen, and they could talk to each other and move these spots around, which I don't think you could do now. And he also had this thing, this five-fingered chord keyboard, which he was actually using to give commands to the word processor. And it's a bit like the microwriter, which I was sorry disappeared. It's worth digging this out and watching it, probably. But here, just going back to the wheel of reincarnation, this is very much a central computer with all the work being done by the computer. And all these guys back in the lab tweaking things, I suspect, as well. And one of the other predecessors to Xerox PARC was Alan Kay with the Dynabook. And now we've all got a Dynabook, haven't we? So PARC itself was started in 1970. We forget at this time that Xerox was an enormous, very powerful company. Every office had a Xerox copier in, but nobody else knew how to do it. And just about this time, I think, the boss of Xerox went out and bought SDS computers for nearly $1 billion. It was $900 million he paid for this computer company. It gives you some idea of the amount of money they had. So they decided to set up a research centre and recruited people from all over the place. And one of them claimed that it was the best computer science research establishment in the world, which may well be true. There were, I think, 3 different departments. And the department we're talking about here, I think they're called the Computer Science Department, and they were responsible for Alto and one or two other things besides that. So the Alto was proposed to be a personal computer, and here the reincarnation has gone the other way now. It's gone into the thing that was sat at, the computer was sat at. And this looks a bit unbelievable, but from what they say, is it was proposed and designed and working in about a year, which seems a bit unlikely, but anyway, it can't have taken very long. And in the lab, we're going back now to the Xerox PARC itself, they had Ethernet, which I think was invented either there or at Stanford. I'm not sure about that. They had a large character generator, which was needed, I think, to drive the laser printer, which was also invented there. And they had servers, which were actually these some of these SDS computers which the company had bought. In 1976, the first Alto office use that took place in a book publishing company which belonged to Xerox, so it was an easy setup. And they were provided with a word processor which looks like a modern version of Microsoft Word. They eliminated all the keyboard commands that were built into their original. There weren't many, but they had some in their original word processor, which I think was called Bravo. And in another division of Xerox, people were still working on the Engelbart design of having everything in the main processor and dumb terminals. And this first proper use of the Alto killed off that project, and it died. Now, here, let's just go back to these pictures. This is what you see of the Alto. It's got a screen on the top. The right way around, in my contention, the horizontal screens are a darn nuisance. There's a 2.5 megabyte disk underneath, which is removable. You can pick it off. And then the computer itself lives at the bottom half. Here we have, I'll point to this screen for a change. Here we have an example of their use of windows. I don't suppose they call them windows. We can have overlapping windows on the screen. And the hardware was there was just about the right sort of components to make the hardware. It had a bitmap display. And that used half the main memory up to hold the bitmap. It had a 64K main memory using Intel 1103s. Those of you who might remember these. And they found they didn't work very well. They had to weed out the bad ones sometimes. It had a 1K microprogram, 36 registers, a large constant memory. And as you'll see in the next picture, they used task switching, so they didn't have to dump all the registers and reload them with other things. You'll see how the task switching works in a minute. And the task switching also meant that they could build the peripheral controllers, and there weren't many, into the actual hardware of the CPU. The removable disk, and it had an Ethernet. So here's a picture. Sorry to you guys on that side of the room, I've got to point a little bit up here. This is the secret of the task switching. This is the microprogram here, and there were 16 interrupts you could have, which went to the task register here and changed the location of the place we're working in the microprogram. So there was a microprogram for the disk controller, a microprogram to refresh the screen, a microprogram to refresh the memory, and so on. And I assume, I haven't read this anywhere, but I assume they had enough registers here to accommodate all these different processors just by leaving the registers loaded up, and you switch registers when you switched to a different part of the microprogram. The other significant thing here is down here, the main memory started off with parity built into it, which is how they found the problems with the 1103s, and then they went on to an error-corrected memory. And there's a video of the software guy talking about this, and he points out that PCs never have parity or anything on their memory, because if something goes wrong, they can always blame the software people, not the hardware people. So, that's why we don't have parity on our PCs. And this is the design of the whole machine. We haven't got freestanding controllers for the peripherals. It's all there in that little box underneath the display. Okay. They emphasised that the software for the Alto was there to be used. It wasn't to demonstrate anything. With a word processor and networking and all these things was meant to be used. They used a language called BCPL, which is in the microprogram PROM, but you could choose other languages if you wanted and load the RAM up with emulators for them. There was an emulator for Smalltalk, which was there for doing clever things. Smalltalk was produced by Alan Kay. And this thing called BitBuilt, if that's how you pronounce it, where you could maneuver bits of the bitmap, areas of the bitmap. And this is how they solved the problem with the overlapping windows. The word processor was WYSIWYG. You could see what you were doing on the screen. You could have different character sets. They did a lot of emailing because everybody had an Alto. These things were produced in large quantities. Everybody had an Alto. And when they got onto things like VLSI and so on, there were VLSI applications running on it as well.
I think that slide BCPL was used in the prototype Altos. Most of the production software, including Bravo, was done in a language called Mesa, of their own invention.
Oh, okay.
And the locals call that instruction BitBuilt, the Americans and actor.
Right, okay. As they come over, obviously I know nothing about software. So now then, in 1979, Jobs, no, it was the Xerox financial people went to Apple and said, we want to invest in you. And Jobs said, well, we could sell you some shares, but you've got to reveal what's going on in Xerox PARC to us. So, much to the anger of people in PARC, the financial people said that we've got to show these guys around. So, there was one visit where they were shown, and Jobs took with him all sorts of people who knew what they were after. Whether he said these remarks at this visit or his second visit, I don't know. But Jobs said all these things. But they went away after the first visit very dissatisfied because they hadn't actually been shown anything. And then they went to the financial people and said, we want to know what's going on. So they had to have a second show where things like Smalltalk and BitBuilt and all these things were revealed to them. And we know, of course, that went into the Macintosh. Sorry, go back. The management never wanted to sell the Alto. There was a thing called a Star, which came about a few years later, which wasn't the Alto rejig, it was a different machine. So this machine was produced in large quantities. Everybody in Xerox had one, but it was never sold. So it qualifies for this talk. Okay, now, 1976, when you're struggling to design a large computer, it's not a particularly pleasant experience. And when it was finished, I certainly started thinking, well, suppose we threw all these fancy instructions away and all these fancy ways of accessing memory and so on, and produced a nice, simple machine. It'd probably go twice as fast. And if you want to do division, you've got to program it, and so on. And we knew of the existence of the IBM 801, but not what it did. But it did seem to be what's come to be called a RISC machine later on. And so this is the story of the IBM 801. Small team of people, both hardware and software people. Software people were compiler designers. They had 10 years of IBM 360 instructions to look at and see what the frequency of instructions was like. They decided to use lots of registers and load and store. And what this means is that you don't have instructions which take data out of the memory, multiply them, and then put them in a register. You either load a register, pure and simple, or you do arithmetic. And you separate out operations on registers and loading and storing them. And this is one of the characteristics, apparently, of a RISC machine. The next thing, which speeded things up no end, was that there were separate instruction and data caches. It's Harvard architecture machine of sorts. There was no microcode, it was a hardwired machine done by a small team of people. And this is where Mr. Cox surfaces again. He seemed to be the project leader of this, and he was getting on a bit by this time. But it was a simple but extremely clever design. It was intended to go in a telephone exchange. It wasn't intended to be a data processing machine at all. I think that bit of it got forgotten about. Now in 1980, way after this time, Berkeley invented the RISC machine, which was already in existence in the form of the 801. And here's a very nice, simple diagram. We'd all love to make a machine like this, wouldn't we? You can see how the thing works. Got two cache interfaces, a data cache interface and an instruction cache interface. Got lots of registers, simple arithmetic unit, not much more. And there was no microprogram, so you've got the instructions that were hardwired in. And this is what it looked like. Here's Mr. Cock with the, this isn't the whole machine, by the way, there are about 6 doors, I think. The prototype was made in wire-wrap TCL. It had 10 logic stages between clocks, 6 to 9-second clock. The cache access was the same as the clock period, so that was great. What I'm saying at the end is, when you go and make one, take the diagram and get onto the RS website and have a go. Right. How are we doing for time? Oh, we're doing okay. Wait a minute, you've skipped something here. Here we go. There's a slide out of place, so never mind. In 1982, the Japanese launched what they call the 5th generation computer project. Now, up to this time, MITI, the Japanese Ministry of Information and Trade, had been extremely successful. It started off, I think, with motorbikes and produced all sorts of things and really invested properly into Japanese industry. But somebody dreamt this up, and they decided to put a great deal of money into this, and everybody else seemed to panic. We've got to respond to this. The Japanese are going to take over the world with their computers. So in the US, they launched a company to combat this. In the UK, we have the ALVI program, and the EU launched the Esprit program. Now, for some reason, I was the first representative on the committee meetings that were held about ALVI. And we used to go into the Millbank Tower and sit around this table, and I'm not sure that anybody really knew what was going on. And soon after this, I left ICL, so it was I didn't carry on with this. But these were the aims laid down by the Japanese. Are very ambitious, particularly this Prolog personal computer, things like relational database computer, multiprocessor, all sorts of things. And AI was going to be the future. Now, if you follow the history of AI, it's had great ups and downs. There's an article, it might be the Wikipedia article, that talks about AI winters and AI springs and things. And so I can remember an article in, I think it was the Communications of the ACM way back, which called the artificial intelligentsia. It was a very sarky article about artificial intelligence. And then there was the Lighthill report, which poured cold water on it. And I suspect it was rather down at this time. Now, of course, it's in the paper every day. If you watch The Good Wife, anybody watches The Good Wife? No. There was an episode last week of a court case where AI was discussed in great detail. So it's everywhere. But at this time, I don't think it was. I might have to go back to that slide now. I don't know how it's gone on. No, let's go back. Don't know how this jumped. The Alvey programme was the British end of this. A great deal of money was put aside for this. I don't know quite how much was spent. And I don't know how much thought was put into what do we get back for spending. It was spent £350 million on this sort of thing. ICL had a go at a prologue computer using transputers. I think that was working. But then, after 1985, everything goes quiet. You can't find out any more information about what went on. Brian Oakley, who was in charge of the programme, wrote a book about this, which I must admit I haven't read. But I suspect that the results of this, and maybe people here can put me right, were very much like the Japanese, that they didn't really get anywhere at all. And it certainly seemed to have sunk without trace. And the Japanese, they were rather clear about this. They spent at least $200 million. They built 5 machines in different universities. Got working. Moore's law was pushing them out of the way, really, because you could make achieve the same results with conventional machines. And their state, it was terminated without having met its goals. And there were obituaries being written in 1982. So lots of computers here which never got to the marketplace, and it's not clear quite what they were meant to do, to me anyway. Now, in, I think it was probably about 1991, 92, I had a phone call from a friend of mine who works at Manchester University called Alistair Rawsthorne, and he said, there's a job going in France. If you want to go out to Lyon and have an interview, you might get a job with these people. And so I said, well, what's going on? He said, well, they're going to build a supercomputer. And what's more, there's a magic ingredient in this from Manchester University. So I swanned off to Lyon, had an interview, and it was perfectly obvious to me that these people had no idea what they were doing, and it was a complete shambles. And, the headline here, which means the mad gamble in French, this is out of a French magazine. And so, when I thought I would do this talk, I spent a day trying to remember ACRI, A-C-R-I. I couldn't even remember the name of this place. And eventually it came to me. And yesterday I spoke to Alistair Rawsthorne, and I said, what was the secret ingredient? And he ummed and ahed a bit about this, so whether he was kidding me at that time, I don't know, but we'll come to something about Alistair in a minute. So what on earth was going on here? This album was created by a guy called Jacques Stern, who had set up his own very successful computer company, sort of a systems company, I think it was. The government made him head of Machine Bull, the French government-owned, I think, computer company. And there's a Japanese website about this which calls it the Buddha of Bull. The aim was to build a big computer. And I think it was to build a cheaper but nevertheless extremely powerful machine. They got loads of funding, loads of managers. At one time they had 6 layers, which is more than Ford. They had loads of people, partly because they had Esprit funding, who demanded them, they had a certain level of staffing. I don't know what that was about. They were paying out ridiculous salaries, and they were over there in France. And why I've put École Polytechnique at the end of Jacques Stern is you don't get anywhere in France unless you've gone to a Grande École. And the École Polytechnique was a Grande École. and apparently that's part of life in France. Okay, so let's look at the only schematic. I can only find this on a Japanese website, would you believe? There's very little information about Acri anywhere. And what they've gone for here is what's called decoupled architecture. And this was created by a guy called James Smith, who worked for this astronautics company at the bottom here. And they did produce a working machine. His schematic for this ZS1 is much more understandable than this schematic. And the idea is that, and I think this depends on having a very wide memory access, so while I can't see how it works, the machine picks out from the instruction stream instructions to do with manipulating the data and instructions to do with loading up the registers. And these things get separated. And so here we have an address processor, which is looking after the data, lots of queues you can see all over the place. And here we have something which is performing arithmetic and whatever needs to be performed on the data. And in the middle here is this thing called the control processor, which is helping to sort the situation out. So the instruction stream comes along, instructions are picked out depending on what their purpose is, put into different queues, and somehow something keeps track of all this so that the data corresponding to the arithmetic to be performed actually matches up. And I presume in this case it was this control processor was the idea. James Smith's design doesn't seem to have this problem as much. This needs a fancy Fortran compiler to produce an instruction stream. And they have 30 people working on a Fortran compiler. As far as the hardware goes, again, we're getting back to the shambles now. They were going to make the whole thing, I think, out of gallium arsenide chips, which were made by, are they called Vitesse? Is that the name of the, or is that the computer company that used them? Anyway, and they couldn't find a means of mounting these gallium arsenide chips onto anything sensible. And the only things they ever had made, all the chips came back broken. So as time went on, they switched the idea, and I think they were going to make the address processor and data processor out of ECL, and they adapted the DEC alpha processor as the control processor. And the DEC alpha logic was actually going to be faster than the ECL logic. So why they didn't make the whole thing out of VLSI, I do not know. So the chaos and shambles persisted right to the end, and they went back up to 1995. Now, going back to Alistair Rawsthorne at Manchester, these weekly shifts of things at Acri, and I think they had 5 different instruction sets from time to time, made him think about this, and he went back to Manchester and created, and I don't know what this does, so please don't quiz me about this, but it's a system whereby you can translate from one machine code to another machine code. And it works extremely well. It was sold to Apple when they switched to Intel processors, and it is in every Apple computer that you buy with an Intel processor. And I think they've sold off the company to IBM. But it was an extremely successful project, this. And it was created out of the chaos that was going on in Lyon, of not deciding what the instruction set was going to be. Oh, okay for time. Now, I'll just finish off with a return really back to the asynchronous business we started at the beginning. If you read Mead & Conway, it's in there because Ivan Sutherland, who was at Caltech, was very keen on the idea. And what asynchronous logic is about is that in a normal computer, there's a clock on every single flip-flop, and it's the same clock. It has to be distributed everywhere. Apparently in that DEC Alpha chip, it takes up a third of the area of the chip to distribute the clock. You can throw that away if at each stage of doing things, you can detect the completion of what you're doing, clock that into the flip-flops where the result's going to go, and then go back again and say, right, I've done that, send me the next thing along. And this is a grossly simplified version of what it's about. You push the data through the combinatorial logic. Somewhere, it's a thing that says it's finished. It might be something which detects the carriers in an adder, for example. When it's all finished, you clock the next set of flip-flops and send a message back saying, we're done, send in the next data. Now, this has been around for a long time. There was an asynchronous processor of some sort made at Caltech. In Manchester, they've made 3 asynchronous versions of ARM chips, which never got to the market. And it goes on and on. There'll be lots of asynchronous designs, lots of spin-off companies, of course, which didn't come to very much. And the pros and cons are as follows. The pros are you've got no clock distribution, so you save a great deal of power, you save area on the chip, you can do it like-for-like processor, ARM chip. Asynchronous chips are about the same size and similar performance. They've got low electromagnetic emissions, which we'll come to in a minute. You've got low sensitivity to power variations, and I think this was the Caltech thing. You could take the Caltech asynchronous processor and put a hot cup of coffee on it, and all they did was slow down. And you can't do that with a conventional micro. Well, you could boil your coffee, couldn't you, with salt and that? And it should also, and I don't know what these might be, but it should also bring up new ways of doing things as well, not just CPUs to do data processing, but other things. Things against this are no designers are trained in doing this. You've got to have a whole new set of people who know what they're doing. Design tools have become very advanced for VLSI designs, and there are less tools for doing asynchronous design. It's more difficult to decide whether you've got it right or not. It's more difficult to verify the design. And if you go to your management to say, oh, we want to make asynchronous machines, they've got to see a clear advantage in doing this. It's not easy to do that. But just going back now to the electromagnetic interference and the power thing, if you take an ordinary credit card and put it in a rig of some sort, switch it on, and monitor the power consumption of it on a scope, presumably. I didn't realise this till yesterday, I thought it was more complicated than this. If you put in 1 to 10 as the pins, the first digit of the pin, when you hit the right digit, the power will dip or go up. Something different will happen in the power that you see on the scope. So you've got number 1 digit, do the same again you get a dip. So it's just like fiddling with a combination lock. You know, you can pull it and decide what the pins are. You can do exactly the same thing with a credit card, just by monitoring the power. And I think you can probably do something similar by monitoring the electromagnetic thing as well. Now, I don't know why, because it would seem to me this would also apply to an asynchronous design. I don't know why, but the asynchronous fans say this is much more difficult to do with an asynchronous processor in your credit card. And the other thing about credit cards is, and we've probably all got it in our pocket. I cannot find out what's going on there. When you wave your credit card at the terminal in the supermarket, there's a very small amount of power going into that processor, isn't there? There's some sort of radiation comes off to power up the chip. And if you can reduce the power consumption of that chip, then you're getting something. So it's quite possible that we've all got asynchronous microprocessors in our pockets. But I can't find out about that. So there we go. Right, here's the book list. Get all these read before you get the test papers. I've said this before, that Samuel Smiles writes great books about Victorian engineers. He's like the Vasari of Victorian engineering. He knew these people, talked to them. And in this particular book, there's an appendix where Babbage talks about the first visit he made to Clement's workshop. They had a lathe in his kitchen. This is the Swedish book about different engines. Quite a nice read. 2 books about Park. The Dealers of Lightning is a Pulitzer Prize-winning book, so it's full of stuff about personality and so on. It's about so thick, but it's quite good. Another one about Xerox Park. Unfortunately, neither of these people are technical, so you don't get much feel for the technical stuff. And of course, I can't resist saying VLSI systems. Can I just finish up with an anecdote there? I went to see a friend of mine who was working at Caltech, and he wheeled me in to see Carver Mead. Now, he's one of these people who just talks at you. And one of the things he said, going back to this credit card thing, he said, if you look at the average American home now, there's 30 electric motors in it. And he said, we'll get to the stage when there are 30 computers in it. And start counting, folks. But the first thing to count is the stuff in your wallet, because each one of these has got a computer in it. And he gave me a Xerox color copied version of this book, and I brought it back to West Gordon. It hadn't even been published at that time. It was all beautifully bound, and so it was a Xerox copy. So there's the anecdote. So that's it. Thank you very much.
Thank you very much indeed, David. Does anybody have any comments or questions? Terry?
I just put a date on this asynchronous issue. I remember at the University of York, which was in 77 and 78, attending a lecture, the topic of which was, can computers service interrupts? And it was given by somebody famous from Cambridge.
David Wheeler.
I think it was Wheeler, because Wilkes denied it when I asked.
And it was an examination question when I turned up in Cambridge in 75. It was always in paper 2, section. And the student humorous version of it was explained by an asynchronous lecturer is unstoppable in 50 minutes.
Yeah, I heard that somebody in Cambridge, presumably is David Wheeler, had a list of 20 micros that had this problem in them. The Z80 certainly had, apparently.
It arose in EdSAC too.
Yeah.
They discovered the metastability in
Yeah,
design
yeah.
the machine.
And it's why when you pick the telephone up, you sometimes get a cross line, because 2 people pick the same,
Yeah.
try to get the same instruction.
Yeah.
Even if you put
It's a bit terrifying, isn't it, when you learn that Trident missiles are run by Windows and because you've got this all over inside relationships.
The same is true of aeroplanes. And I actually had it happen to me. I was flying my aeroplane one day and there was another aeroplane coming the other way. And do I think we're close enough together to both turn right or slightly further apart we're going to pass?
Yeah, yeah.
I'll be down.
Yeah. Ships can't do that.
Hit the ceiling. Not as easy with ships, you know.
That's called thumbnail.
The ICL 1906A was asynchronous. And it would,
So the ICL...
1906A was asynchronous. And it would occasionally come to a, I'm going to say a grinding halt. In fact, it was a sudden halt. And the official engineer's explanation was, I lost 3 pulls. So you had to start it up again. And I thought I asked Steve Ferber about the arc shift, and I couldn't say that was asynchronous.
But the 6A is listed in the Wikipedia article about this. And I don't know, I can't believe it was really asynchronous. I read something about the clock slowing down in certain occasions when you had to slow the clock down. which isn't quite the same. No, but I don't know. So, Chris?
First thing I mind back to ICL and the Albi project.
Yes.
I think you were a little bit dismissive about any outcomes from that. I know, of course, it wasn't designing a machine on the drawing board and then scrapping it, but ICL did run a knowledge engineering department for some years, which was stuff like people who had been on the Albi project and had last learned about expert systems and so on, and were marketing on a small scale these things, expert systems essentially, some of which were written in Prolog, some in Lisp. So there was some outcome.
I should have warned people about my prejudices as well. But they were running on conventional hardware, though. That's the point, isn't it? They weren't delivering a Prolog machine to do that on.
So there are a number of us at that time in academia who realised the sensible thing to do was ride with Moore's law on the hardware and just buy commercial processors but do clever things in software.
Yeah, I'm sure. Yeah.
And there are a number of commercial spin-outs, and I took £3 million out of Albi plus £1 million of Esprit.
I knew
And
there was
I
somebody
gave
here.
back 40 million to the UK government, an American company, took it over. So that was quite a good return on investment. There were many other examples.
Yeah, you mentioned the IBM 801, which you described as a RISC machine, and in particular you said that each instruction either does the register to store transfer, or vice versa, or does arithmetic. That is exactly what the control data 6600 does, which is why RISC actually stands for Really Invented by Seymour Cray.
That's a point made elsewhere that the 6600 was. It was everything, wasn't it? That's a fantastic machine.
I have a story about the Acri machine, which I will tell you as long as you promise not to take it into account when you vote for Brexit or not. I was a reviewer for Albi projects, and the review team used to be from all the countries that were concerned. And we could never agree about anything, really. We had majority votes. And Acri came up at one of these for its follow-on. It was in two sections. It got money for the first part, and then the money for the second part, and we had a review for the second part. And we were unanimous in saying it should be stopped. This caused enormous consternation among the political people who were surrounded, and in fact they got their money for the second part.
But probably Grandier Collins probably.
Absolutely.
I'm a software man, so it's probably a really stupid hardware question, but when you were talking about the IBM advanced computer system, it had a memory cycle time of 10 nanoseconds, and you said you had to pipeline things because you couldn't do very much in 10 nanoseconds. Right. So what was the point of having a cycle time of 10 nanoseconds?
Good question. I don't know. Just a little bit more of a personal anecdote here. When we were doing 2980, we had a clock period of about 100 nanoseconds. And at MU5, I think they were aiming for 35 nanoseconds. And Roland Ibbott, who was my was the Manchester University person, the equivalent to me, we used to have arguments about this because I used to say you can't do anything in 35 nanoseconds. I suppose the benchmark got to be a 64-bit floating point adder or something. If you can't do that, you can somehow split that up into pieces.
Yeah, but that's what Cray was famous for, right? On Cray 1, all the functional units were segmented. So an add took 5 cycles, and then multiply 6, so you had to divide took 56. So once you kind of loaded it up, it took you several cycles, but then out of the pipeline you're getting one result every cycle.
But that was because it was a vector machine.
Yes, but the functional units were segmented. Right, so they classically this.
You can do that with vectors because you know you've got more coming on.
Yeah,
it's just a random set of instructions.
But the other interesting thing about Cray 1 is exactly it's an extremely fast scale machine. So even if you didn't use the vector registers, it ran very fast. Because of that segmentation.
Okay. Well, maybe a bit of Craig cleverness injected that would have made the 10 nanoseconds work well.
I've got a couple of anecdotes. One is to do with the Acre, which I didn't know about. But round about that time, Métier France and the French Research Institutes had bought a Cray 2, which is the one where you just sank it into a big fish tank, cooling loop, liquid. And Métier France tried to share it with the research community and proved it didn't work. So it was a very expensive mistake. But basically, we're doing forecasting, you just have to sort of stop everybody and start the forecast out. Researchers, you tell researchers they have to put stop checks into their software, didn't they do, right? And they just lose 3 months' work. And so I think that may have actually fed into that project because it was quite expensive at the time. And it was about the same time after some research and they were buying. And the other thing about the Alvi and the prologue, we were approached by Imperial to do a lot of prologue and artificial intelligence and backward chain of logic to do weather forecasting. It was Bob Kowalski. And he was a bit miffed because when we said back to him, he said, well, actually, it's all very well doing all these heuristics and backward chain of logic, but actually it's much cheaper to solve force equals mass times acceleration.
Any more questions or comments? Dan?
About the time of the Atlas birthday celebrations, I attended a talk by Steve Ferber about what was Manchester going to do next. And he came up with this SAIL project, which are multiple ARM chips all working together or something.
A million ARM cores.
Yes, I mean, has that ever got anywhere?
It's still going on as far as I know, yeah.
I wouldn't know. I'm a software man as well. You know, this is black magic to me.
He's somehow going to make this behave like a neural network, and I have no idea how that.
I went to a talk by him about a year ago. It was certainly very much alive in his mind at that
Oh
moment.
yes, I think it's going on. It's they built the chip, I think. Has it got 8 cores or 16? I can't remember.
I think it was only 4.
Okay, whatever. It's got a lot of chips on
I
it.
did go to the talk, but remembering these things is becoming increasingly difficult.
Join the club.
Well, thank you very much. Oh, sorry, you've got one more.
I was involved in a project that was to do with Esprit and I think Alvi as well in 1991.
Yeah.
And that was, I'm afraid that I've been trying to recollect the details to form this into a coherent comment, but it was something to do with a machine called the European Database Machine or Database Engine, something like that. Some unholy combination of SQL and Prolog. And I never saw this machine, but what we were doing was more theoretical Prolog around the site, but I get the impression it was supposed to be a special purpose database machine. I don't know if anyone else knows about this thing. I have a feeling I got the name slightly wrong, but it was definitely European database. And that was 91, so deafening silence, obviously. Probably sunk without tracks.
Maybe it's to use up the ISA research with memory.
Yeah, possibly.
Right, sorry for missing anybody else. Right, well, thank you very much indeed. Thank you, David. Thank you. Now, our next event is going to be held here on Wednesday, the 27th of April, not the normal day of time. And it's called Birth and Death of the Basic Language Machine, and the speaker will be John Eilif. And the basic language machine was the first general purpose system to break completely with the concept of a linear address space, thereby offering automatic storage management and precise security environments. And it was unusual in other respects as well. And John Eilif attended the EDSAC programming course in Cambridge in 1952, and his career in IT took him to various places in the States as well as in London, working with IBM and with various academic appointments. And he was awarded the Harry Good Memorial Medal by the IEEE Computer Society in recognition of his work in 2000. Now, all events are announced at our website, and that's where you can pre-register. Please do. and I will also announce the date and time of the next one at each meeting. And I've also just been asked to tell you that there's an exhibition called Big Bang Data at Somerset House, which closes at the end of this weekend, and it's recommended. So anyway, thank you very much for coming, and any comments, do email us.
Thank you.
Excuse me, is registration compulsory?
It's not compulsory, but it's just very, very helpful for numbers for